Okay, so equations in this form. What is this form? What do we call equations that are written like that? That is slope-intercept form. And the reason that it's called slope-intercept, anyone know why?
It's the intercept of the slope.
Clarify that statement. Why do you think we call this slope-intercept form?
Because the slope and the y-intercept.
Yeah, I can easily identify the slope and the y-intercept of this equation. Okay. So we know that when equations in the form y equals mx plus b, they give us a straight line when graphed. Okay. And everyone write this down, because now we're starting to talk about what makes something linear versus nonlinear. If the graph of a function is a straight line, it is called a linear function. The straight line indicates that there is a constant rate of change between any 2 points. Primarily, we've been working with these types of functions so far. We've been looking at the rate of change in our tables. We've been looking at the slope on our graphs. They're representing the same value. That change has been constant. And that constant change is what's making our lines straight. So as you're writing, if you're thinking about linear functions having a constant rate of change, you could probably assume what type of change a nonlinear function might have. If you know that a linear function is constant, what do you think a nonlinear function would be? Not constant, exactly. And we're going to spend today identifying what that would look like in an equation, in a table, and in a graph. So what's in red, we should have written, if the graph of a function is a straight line, it is called a linear function. The straight line indicates that there is a constant rate of change between any 2 points. Can I advance the slide? Straight line indicates there is a constant rate of change between any 2 points. So let's take a look at this graph.
I didn't get to finish.
Oh, sorry. Real quick. It's only 2 sentences. Now on the next slide, we're going to graph. We're going to work on graphing an equation that's not in slope-intercept form. So some of you already saw it. Think about how we would graph a line. Where we need, how many points do we need? How do we find those points? Are you good now?
Yeah.
Okay. So now normally we have equations like this. We've seen so far equations in slope-intercept form like that. How would I graph that line, this equation up here? How would I graph this? What would I do?
What would be your line?
I can plot my y-intercept, absolutely. And what value of this equation represents the y-intercept? The 4. Yeah, this value. So there's my y-intercept. And how do I get another point on the graph? I'm going to use the slope. How am I using the slope to go from this point to my next point? What is the slope?
3.
The slope is 3, which means how am I moving? Up 3 over 1. This number here, if you need to make it into a fraction to really see that rise over run, you can do that. If I have this second point, I now have my line, and I'm good. But this equation here is not in slope-intercept form. 2x plus 3y equals 12. How do you think we can graph that line? Okay, you have 2 options, right? There's 2 ways that we can graph this. But the main question here, and this will help you figure out how to graph it, what does it mean to have a coordinate on a graph? Like if I say I have a point on a line, what does that mean in terms of the equation? How would I know if the point is on the line or not on the line? could you tell me one point that is on that line? So is that a point? Is that a coordinate? Think about what makes up a coordinate.
2 points on the grid. X, Y, X, Y.
An x and a y. An x value and a y value make up a coordinate.
Yeah.
Right? So if I see a coordinate like 0, 0, I know that that's where, on the graph, where x is 0 and y is 0. And that point here just so happens to be at the origin. Right? So how could we find a coordinate on that line?
Maybe a coordinate could be 1, 2.
Okay, how would that, how do we know? Could you prove it? X is 1, y is 2? Okay, so Laura thinks that x is 1, y is 2. How would we prove that?
Where'd you go?
How can we prove that a point is on the line?
You can plug in,
What do you mean plug in?
like, right now.
What were you saying, Joe? I can substitute for x. Okay, so Jordan said plug in, and Joe said we could substitute for x. What value could I substitute for x that might be relatively easy to calculate?
2.
I'm just going with Joe. I heard him say 0. If x is 0, what's y?
1,
1,
3, 2, 1.
3. Eric, how do you know that if x is 0, y has to be 4?
It's not just 0, 0, and 3 times 4 is equal to 2.
Good. Eric said because 2 times 0 is 0, and then I can solve for y because 3y equals 12. If I divide both sides by 3, y would have to be 4. So I found a value. Could I find another value? Do I always have to substitute for x? Now, if I had an equation in this format, this is not slope-intercept form. This is standard form. So you might see, especially in your next unit, equations like that when we're solving the system. You can always substitute values to find a coordinate because what does it mean for an x and a y value to be a coordinate on my line? How do I know that 0 and 4 have to be on that line? And when I substitute, what happens?
on your line.
Like if I put in an x for 0 and y is 4, what happens to that equation? So 0 plus 12 equals. What do I get when I plug in a 0 and a 4? What does that do to my equation?
Makes it equal.
It makes it equal or true. It makes it true. Okay, and that's every coordinate on a graph. That's why those points are on the line, because when that x value and that y value are together, they make the equation true. Do I always have to substitute in for x? Could I substitute a value in for y and maybe get another point? Because how many points do I need to graph a line? I only need 2. I already have 1. Could I plug something in for y that might be relatively easy to calculate? If y is 0, what would x be? 6. Because 3 times 0 is 0, and then 2 times a number gives us 12. That would have to be 6. Do I have a line now? I do. I can plot 0, 4, and I can plot 6, 0, and create my line. That is a way we can create an equation, a graph, using an equation. If it's challenging for you, if you don't have it in slope-intercept form, you could substitute values in. Now, earlier in the day, some students wanted to substitute in x for a 1. You can do that. If x is 1, y would end up being 10/3. That's still a value on the graph. Some people don't like working with the fractions, and I totally get that, but you could still get values on the graph. Is that the only way we can graph this line? What else could I do? And I want you to channel back to Unit 1. How else could I graph, if I know really confidently how to graph an equation if it was in this format? I know how to graph a line in that format. What can I do to my current equation to make it easier for me?
Put it in slope.
I can actually put that equation into slope-intercept form. What would I have to do in order to get my equation into slope-intercept form? What variable do I want by itself? I can get the y alone. Did we do that last unit? Did we learn how to solve for a variable if there were like other variables around? What did we call that? Anyone remember what kind of equation that was? What? Literal, yeah, that's a literal equation. What would I do to get y by itself? What would I get rid of first? I can subtract the 2x from both sides. So I would have 3y equals 12 minus 2x, and then what? And then divide everything by 3. Is that in slope-intercept form now? I'm going to simplify 12 thirds and make it 4. Is that in slope-intercept form? Yeah, I mean, it's flip-flopped. But could I still identify the y-intercept and the slope?
Yes.
Absolutely. What's the y-intercept? 4. Which was true. I had that already from substituting it. And then what's the slope? How can I use the slope to get another point? So how do I move? Down 2 and over 3. And look at this. If I go down 2 and over another 3, I'm actually at 6, 0. Which was another point I identified earlier as a point on my graph. So whether you substitute values in to find a coordinate, or if you put the equation into slope-intercept form, both will work. Okay. Some students really love slope-intercept and are confident with literal equations to rewrite. Others may not feel as confident and want to work with a table. Okay. Either way is good, but the reason we're starting with that table today is because now we're going to graph a line like this. How would I graph that line? What values are going to be on that line? Can anyone give me one coordinate that is on that line? Zara.
0.
If x is 0, y is 0. Can someone give me another point on that line? Can anyone give me another coordinate?
1, 2. Y is 4, x is 2.
If y is 4, x is 2. I'm going to move it. We have some other ones too. Yeah, if x is 2, 2 squared is 4. What else can I put?
4, 16.
If x is 4, y is 16. Good. I'm going to move that right there. What if x is 1? 1. Y is 1. What if x is 3?
9.
Y is 9. Can I graph that? Yeah, I already have the points. I have 0, 0, 1, 1, 2, 4, 3, 9.
Whoa.
Whoa.
What do you know about that? Now, I can prove this as well. If x was negative 1, what's y? What's negative 1 squared?
Negative 1 squared.
Is positive 1. What's negative 2 squared?
4.
Yeah, negative 2 times negative 2 is positive 4. That's why this parabola, it's symmetrical across the y-axis. We'll learn that in the spring on like what makes that do that.
I remember seeing that.
Okay, so, is that linear?
No,
No. How do I know?
because it's not going
It's not constant.
straight. It is not constant.
So I have a few ways that I can prove this, right? If I look at the graph, can you tell me looking at the graph that it's not linear? Correct, it's not a straight line, right? All of us should be able to look at that graph and say, I know that that's non-linear because the line isn't straight, right? It's not, this is a curved line. How can I prove that it's not linear in the table? Because for most of us, we can look at a graph and say if it's straight or not. Okay? But on an exam, you're probably going to see it in a different format. You would probably see on the park, it would probably be in the table or maybe the equation. So we're going to learn how to identify in the table and the equation what makes it linear versus non-linear. How do I know in the table? Pretend like you don't even see this image. How do you know in the table that it's not going to be a straight line?
It doesn't have a constant.
It doesn't have a constant rate. How do I find the rate of change in that table? What else do we call our rate of change? In a graph, it's our slope. And how else can we how do we find it? It's what change. The change.
Oh,
In Y over
The change in y compared to the change in x. So if we look at the table here, is my x value changing consistently? Yeah, it's increasing by 1. So we're good. So far, so good. Okay. What's happening to my y value?
It's going up by 3.
It's increasing by 1, and then by 3, and then by 5, and then. So what do you notice? Is my change constant? No. My change in y over my change in x, it was 1 over 1 here, 3 over 1 here, 5 over 1 here, and 7 over 1 here, which means in between each coordinate, the slope of each is changing. That's why this increase is different than this increase, which is different than this increase. That's what makes it a curved line. So in the table, and when you go through a table, make sure you're checking every value, because how many values would need to be different for a relationship to be nonlinear?
I don't know.
1.
Only just one, right? If my change was like 3 and 3 and 3 and 7, then all of a sudden that's not going to be linear. So the graph of y equals x squared is not a linear function. The graph is not a straight line. This should say straight line because it is a line. This is another example of a function that is nonlinear. Okay? How did we get the values in the table? This is y equals x squared plus 2. You notice it's actually the same graph from the previous slide, but what's the only difference? Yeah, it's y-intercept. It moved up, but it jumped up 2 units. We'll learn that in spring. How did we get the values in this table? Yeah, substitution. If x is 0, 0 squared is 0, plus 2, y is 2. If x is 1, 1 times 1 is 1, plus 2 gives us 3. If x is negative 1, negative 1 squared is positive 1, plus 2 is 3. And these values are here. Again, you can see on the table that the growth is not constant, and I can check it. My x values are increasing by 1. That's not the issue. My issue is here. What's the change for my y value? -5, and then -3, and then in order for that to be a straight line, each one of those values would have to be equivalent. And now we don't want to focus on it being the exact same, because what if I left out a coordinate on my table? The growth has to be equivalent. We'll look at examples of that. Can you give me an example of an equation that is linear? We know it's going to be a straight line. Can you give me an example?
1 over 1.
Is that an equation?
Oh.
Think about the format of the equations we've used. Can you give me one that you know would be a straight line?
Y equals 3x.
Do we know that's a straight line? Yeah, can I prove it in a table? What values would exist in the table? 0, 0, 1, 3, 2, 6, 3, 9. The growth is constant. Every 1x, I'm increasing my y value by 3. And there are a ton others that we can look at. So we can graph to tell whether a function is linear or not. Most of you have seen a graph at this point, what represents a straight line and what represents a curved line. So we're pretty good now. We've seen a straight line and a curved line in a graph. We've identified it in the table. How about this graph? How would I figure out if this is linear? Y equals x to the third. Can you fill in the table and tell me the values? Do we know any values here?
8,
Which one?
-2,
If x is -2, what's y?
8. Is it 8? It's -8.
Yeah, because you multiply.
Oh, there's 3 negatives.
Good. Do we know any other values?
Negative 1.
Which ones do we have?
We got a 1.
If x is -1, what did we come up with?
Negative.
Y is -1, good. What about x is 0? 0. X is 1. Y, x is 2. Alright, so we have this, 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 this. Is that a function?
No.
Yes,
Yes.
Why? Why is that a function?
because every input has one output.
Because every x value still gives me one y value. Is that linear?
No.
No, you can tell by the graph. You can also tell in the table. Because look at this growth. I'm going up by 7, I'm going up by 1, I'm going up by 1, I'm going up by 7 every time my x value increases by 1. If you feel really confident identifying linear versus nonlinear in a table, that's fine. If you're confused at any point, you can try to graph the point, especially if you're given coordinates. So we've identified how to figure out if we have linear or nonlinear in a graph by looking, and also in a table by finding the change. Now let's talk about just the equations themselves. The equation on the left, is this linear or nonlinear?
No.
Was this linear or no?
Oh, it is.
Yeah, this was linear. And how about this one on the right? Nonlinear. How are they similar? How are these equations similar?
They do grow.
Oh, they still grow. Both grow.
It's not constant.
They both grow. What else is similar about them? They both have an x and a y. They are both functions. How are they different?
One has a slope on the while the other one doesn't.
Is there no slope in this?
There is.
No, it's not.
Are they both growing?
Yeah.
They are both growing. So be careful saying there's not a slope. You're on the right track though. Think about other vocabulary that we can say about differences between these two.
One has an exponent.
One has an exponent.
They have different initial values.
So what's going to happen? They do. They have different initial values, different y-intercepts.
Yeah.
What part of the equation do you think determines if it's linear or not linear?
like the what multiply.
Like why is y equals x to the third nonlinear and y equals 2x plus 1 linear?
Oh, linear.
What do we think about their differences is what makes it linear versus nonlinear? Do we think it's the different y-intercepts? Do we think it's the exponent?
It's like yeah.
Both equations, you're multiplying x by something, right? In the equation on the left, are we multiplying x by the same thing every time?
Yeah.
Yeah, every time I increase my x value, what happens to my y? It's gonna multiply by 2. It's gonna increase by 2. So if x is 1, it's 2. If x is 2, it's 4. If x is 3, it's 6. Obviously, I'm gonna add 1 after that, but this is the growth we're talking about. Every time my x increases, my y value will increase by 2. What's happening over here? Are we still multiplying? Are we multiplying by the same value every time? No, because if x is 1, what am I multiplying by? I'm going to multiply 1 by 1 by 1. If x is 2, what would I multiply by? 2, because I would multiply 2 times 2 times 2. If x was 3, 3 times 3 times 3. This is exponentially growing. It's not growing at the same rate. Prove 1 for I ready today. That's the difference. There's another type of change. There's another type of equation, I should say, that you will see in the activity that we're doing on Desmos, which is the website, in a few minutes, that you'll identify what makes something linear or nonlinear. How are these graphs similar? Are they both functions? Yes, they are. They both still have an input and an output. What do you notice about the growth?
It's I would say it's
The constant scale.
This straight line represents that constant growth, and this curved line represents the growth that is not constant. And the exponent is really what's doing it there. Really quick, take a look here. Which one's linear, which one's nonlinear? Can you tell me, can you raise your hand and give me one one example of an equation here that's linear. Patrick.
Y equals 1/2 x plus 2
Linear, absolutely. Why is that linear?
plus it has constant rate.
It's constant rate, its growth is 1/2. Every 1x, we're growing by 1/2. What else do we identify? Go ahead.
Y equals -2x
Linear, absolutely. Why is that linear, Laura?
because it's constant also.
It's constant, its growth is constant even though it's negative, so the line will go down, it's still growing at a constant rate of -2. What about the other two?
Non-linear.
Nonlinear. Right. What makes these nonlinear? Yeah, the exponents are showing us that while we are growing, we are not growing consistently. We are growing exponentially because of the exponent. Exponentially, yes. We're going to do this activity on a website called Desmos. Let me pause the video so I can explain your login for this.